Thermodynamics 1, Thermochemistry, relationships involving enthalpy changes for reactions. In this tutorial, we will be going over 3 quantitative relationships between a chemical equation and delta H of reaction, Hess's Law, and some enthalpy changes in reactions example problems. Relationships involving enthalpy changes for reactions. The enthalpy change, delta H, is a quantity associated with a specific chemical reaction and is represented as delta H of reaction. 3 quantitative relationships between a chemical equation and delta H of a reaction. 1. If a chemical equation is multiplied by some factor, then delta H of reaction is also multiplied by the same factor. Remember that delta H of reaction is an extensive property that is dependent on the amount of reactants undergoing a reaction. Also recall that the delta H of reaction is reported for a reaction involving stoichiometric amounts of reactants, basically meaning we need a balanced equation. Here's an example. Consider the following chemical equation. A plus 2B yields C with delta H of 1. Delta H of 1, the enthalpy change specific for this equation, is reported as the amount of heat given off or absorbed when 1 mole of A reacts with 2 moles of B to form 1 mole of C. Thus, if this equation is multiplied by a factor of 2, such as 2, the delta H1 is also multiplied by the same factor 2, resulting in 2A plus 4B yields 2C. This is going to impact our delta H as we're going to multiply our original delta H1 by 2. Number 2, if a chemical equation is reversed, then the delta H of reaction changes sign. The delta H reaction is a state function, which means that its value depends only on the initial and final states of the system. So delta H is equal to H final minus H initial. When a reaction is reversed, the final state becomes the initial state and vice versa. Thus, the delta H of reaction changes sign. So let's say we have A plus 2B yields C with a delta H of 1. If we reverse this, where C is now my reactant and A and 2B are now my products, my new delta H2 is going to be the negative of delta H1. Number 3, if an overall chemical reaction can be expressed as the sum of a series of individual reactions, then the delta H reaction for the overall reaction is the sum of the enthalpy changes delta H for each step. This relationship is known as Hess's Law, and we are going to use it a lot in class. Since the delta H of reaction is dependent only on the initial and final enthalpy values and not on the pathway the reaction follows, the delta H of reaction for the overall equation is determined by adding the delta H value for the individual reaction steps. And I know this sounds confusing right now, but don't worry, we're going to do a lot of examples. Let's look at a symbolic one right now. So here I have reaction 1, which is A plus 2B yields C with a delta H value associated with that. And then I have reaction 2, where C yields 2D. Delta H2, there will be a value for that. My overall reaction is combining these 2 initial reactions together. Now, you'll see that the overall reaction is A plus 2B yields 2D, and there's no C in here at all. That's because this C and this C were canceled out. It was produced in this first reaction and consumed in the next reaction, which is why it is not here. To figure out the overall value, we're going to add together delta H1 plus delta H2. So the individual reaction equation with known delta H values are manipulated to attain the overall reaction equation exactly as stated. These three quantitative relationships make it possible to determine the heat of reaction without directly measuring this value experimentally. Let's look at a reaction. Determine the delta H reaction for the following overall reaction. Okay, so this is where I want to get to. This balanced equation right here. I have reaction 1 and I have reaction 2, and their associated delta H values for each of them. So when I look at this, I can see that there's a coefficient of 2 in front of this carbon. That means I need to multiply everything in reaction 1 by 2. Everything here. So I'm going to multiply everything in reaction 1 by 2. Now I don't need to flip it, and the reason why I don't need to flip this around is because this C is a reactant and the C is a reactant right here. Let's look at reaction 2. Here we have our CO over on the product side. In our initial reaction, the CO is a reactant. Now we'll notice that there's a 2 in the product side here and a 2 here, so I don't need to multiply this by anything, but I am going to flip this around. So I'm going to make a little note and I'm going to say flip. Now, what I do to these reactions, I also need to do to my delta H's. So ultimately, I'm going to multiply this delta H1 by 2. In this one, I'm going to change the sign from negative to positive. So I'm going to rewrite reaction 1, distributing a 2 all the way through. So I have distributed a 2 all the way through. Now I'm going to rewrite my delta H1 value as it's multiplied by 2. For reaction 2, I'm going to flip this reaction around. And I'm going to rewrite my delta H2 value so it now has a positive sign in front. Now that I've rewritten both of my reactions and my delta H's, I'm going to combine these two reactions together to see if I can get my overall reaction. So I'm going to put a line like this. Now, what can I cancel here? You could see the 2CO2 gaseous state on the product side, and that's going to cancel out the 2CO2 gaseous state on the reactant side. And I also can cancel out one of my oxygen molecules. I have 2 as a reactant and 1 as a product. So this can go away and this 2 can be removed. Everything else here is unique to itself and also matches my original overall reaction. So when I rewrite this, I will get 2C solid plus O2 gas yields 2CO gas, and that matches my original overall reaction. Now, when I look at these delta H values, I can see that I multiply the top one by 2, and then I reverse the sign on the bottom one. So now I will also combine these together to get my overall delta H of reaction. And when I do that, my value will be negative 221.34 kilojoules per 2 moles of carbon monoxide produced. Let's look at another example. Determine the delta H of reaction for the following overall reaction. This is my overall reaction up here. 2 moles of carbon plus 3 moles of hydrogen gas yields 1 mole of ethane. So I have reaction 1, reaction 2, and reaction 3. The first one that I'm going to look at is reaction 1. And there's 2 things that I notice right away when I look at reaction 1. First of all, the ethane is a product. In reaction 1, it is a reactant. The second thing that I notice is that there's just 1 mole of C2H6 that's being produced, while here I have 2 moles being consumed. There's 2 things that I'm going to need to do to reaction 1. I am going to need to flip this, and I'm also going to need to cut it in half. Let's look at reaction 2. When you look at the overall reaction, you'll notice a 2 in front of the carbon. Here, the carbon is on the correct side, but this whole reaction needs to be multiplied by 2. Reaction 3 is an interesting situation. The hydrogen is on the correct side with the overall reaction. But in the overall reaction, I have 3 moles of hydrogen being consumed, and in reaction 3, I only have 2 moles of hydrogen being consumed. In order to get these equal to each other, I am going to need to multiply reaction 3 by 3 halves. If I do that, then I will end up with my coefficient of 3. So let's get started. I'm going to rewrite reaction 1 flipped and cut in half. Let's look at how I rewrote reaction 1. Originally, we had 4 moles of carbon dioxide. Now we have 2 moles of carbon dioxide. 6 moles of water, 3 moles of water. 2 moles of C2H6, now only 1 mole of C2H6. Originally, 7 moles of oxygen. Instead of making it 3.5 moles of oxygen, I am going to keep it as a fraction, and I'm going to tell you right now that'll work out. So feel free to use fractions when you are reversing these problems, when you're multiplying them by 2. I'm also going to do the same thing to my delta H1 value. I'm going to reverse the sign, and I'm going to cut it in half. So my delta H1 value is positive 1,560 kilojoules. Let's go to reaction 2. For this one, I'm just going to multiply everything in the reaction by 2. I'm going to do the same thing to my delta H2 and multiply the 394 kilojoules by 2, but I will be keeping the sign the same. For reaction 3, I'm going to multiply this entire reaction by 3 halves. Notice here, 3 halves times 2 will give me 6 halves, so I can reduce that down to 3. Same thing here. 3 halves times 2 will also give me 3 moles of water. I'm also going to multiply my delta H3 by 3 halves, but again, keeping the sign the same. Now I want to combine all of these reactions together to see if I can get it to be exactly the same as the overall reaction. But there's one slight modification that I need to make before I get started. Everything works out pretty well here, except for these halves situation. So here I have 7 halves of oxygen, 2 moles of oxygen, and 3 halves moles of oxygen. In order to get all the oxygens to cancel out, I need to take this 2 and I need to change it into 4 halves. And if I do that, when I start crossing things out, the components of the reaction will cancel out. Where should we start? 2 moles of CO2, there's a 2 moles of CO2 on the product side. So those are going to cancel. What do I want to keep? I want to keep my 2 moles of carbon. I also want to keep my 3 moles of hydrogen, and finally, my 1 mole of ethane. Will everything else cancel? Well, I can cancel my 3 moles of water, and then I'm left with 7 halves of O2, and 4 halves plus 3 halves equals 7 halves. So 4 halves plus 3 halves equals 7 halves, and I am left with my original components of my overall reaction. That means I can confidently now combine these delta H values together to get my overall delta H of reaction. So when I combine together 1,560, negative 788, and negative 858, my overall delta H of reaction is negative 86 kilojoules per 1 mole of ethane produced. So what did you learn in this tutorial? We talked about 3 quantitative relationships between a chemical reaction and delta H reactions, Hess's Law, and then we looked at some enthalpy changes in reaction example problems. Need more help? Feel free to contact me. Have a great day.